So this is about the indeterminate form 0 over 0. So what you need to remember here is if you have the limit of a quotient of two functions, like f of x over g of x, then you can use limit rules to say that this is the limit as x approaches a of f of x over the limit as x approaches a of g of x. But that's only true if the two limits exist and the limit of the g of x, the one that's in the denominator, is not equal to 0. So then if the limits exist and the limit is equal to 0, then the limit in the numerator also equals 0. So that means that you would have something of the form 0 over 0. So then you would say that that expression f of x over g of x has an indeterminate form of 0 over 0 x equals a. So here is an example here. 2x squared minus 2 over x plus 1 has an indeterminate form of 0 over 0 at which x value? Well, that would be at x equals -1. And you could verify that because if -1 was x, then the denominator would be 0, but then you need to verify that for the numerator. So 2 times -1 squared minus 2 over -1 plus 1 would be 0 over 0. All right, sine of x over x has an indeterminate form of 0 over 0 at x equals 0. Again, that's where the denominator would be 0, but you can verify that because sine of 0 over 0 is 0 over 0. And then 1 minus cosine of x has an indeterminate form of 0 over 0 at x equals 0 again. So that will be 1 minus cosine of 0 over 0. So that's 0 over 0. Now, these two actually, hopefully you remember that in the very first chapter, we had to memorize the limits of what those were as x approaches 0 because we weren't able to find them because the denominator was undefined there, all right? All right, the expression was undefined because the denominator was 0 there. So how are we going to handle these limits of indeterminate forms? You're going to use something called L'Hopital's rule. So you may or may not have heard of this. This is a famous theorem or famous rule that we have here. So if f of x over g of x has an indeterminate form of 0 over 0, and it needs to be 0 over 0, if you have other indeterminate forms, then we will talk about those in the next section, all right? And then if the limit as f prime of x over g prime of x exists, then the limit as f of x over g of x as x approaches a is equal to that limit right here. All right, notice that this is not the quotient rule. So this is not the quotient rule for derivatives. This is just a special situation where you can find just the derivative of the numerator and just the derivative of the denominator, and then use this to help you facilitate finding that limit. All right, so here we go. So we have the limit as x approaches 2 of x squared minus x minus 2 over x squared plus x minus 6. So let's verify that this is an indeterminate form. So this will be at x equals 2, 2 squared minus 2 over 2 squared plus 2 minus 6. So that's 0 over 0. So because this is 0 over 0, then that means we can use the L'Hopital's rule. If it were not 0 over 0, then we would have to do some rearranging, all right? So that means that this limit right here, this limit is equal to the limit as x approaches 2 of, now let's go ahead and find the derivative of the numerator. So the derivative of the x squared minus x minus 2 is 2x minus the 1, and then the derivative of the denominator is 2x plus 1. And now I just go ahead and I substitute in the 2, so I have 2 times 2 minus 1 over 2 times 2 plus 1, so that 4 minus 1, 3, and 4 plus 1, 5. So this limit is 3/5. All right, so this is equal to 3/5. So that's all that we are doing here is finding these limits. All right, let's try another one here. So we have, now again, remember, this is a situation where we have needed to memorize this one in the past, but here, let's just make sure that this is 0 over 0, so 1 minus cosine of 0 over 0, that's equal to 0 over 0, so that means we can use L'Hopital's rule. So this is equal to the limit as x approaches 0. So of the derivative of the numerator, so the derivative of 1 minus cosine of x is actually, well, that will be 0 minus a negative sine of x, then all over the derivative of x, which is 1. So this is the limit as x approaches 0 of just sine of x over 1, or just sine of x. And then sine of 0, when we substitute in the 0 here, is going to be 0. So this limit is equal to 0. All right, let's try another one here. So we have the limit as x approaches 0 of e to the 2x minus 1 all over x. So let's check for 0 over 0. So e to the 2 times 0 minus 1 over 0. So what is that going to be here? So this will actually be, well, that will be 1 minus 1 over 0, so 0 over 0. So that means that we can use the L'Hopital's rule here. So now let's find the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. So the derivative of e to the 2x is 2e to the 2x. Then the derivative of 1 is 0, so minus 0. And then the derivative of the x is 1. And then we can substitute in the 0. So we have 2e to the 2 times 0. So that will give us, well, 2 times 1, or 2. So this limit is equal to 2. So I really hope that you enjoyed this, but again, just remember that you can only use L'Hopital's rule for cases where you have the indeterminate form of 0 over 0. If we have some other form, then we will need to do some rearranging here. All right, so let's look at the next page where we have repeated use of L'Hopital's rule, or just applying L'Hopital's rule more than once here. So first, again, we need to always check for 0 over 0. All right, so in this one, limit as x approaches 0 of x times e to the 3x minus x over 1 minus cosine of 2x, we have 0 times e to the 3 times 0 minus 0 over 1 minus cosine of 2 times 0. So that will be 0 over 0. So that means I can use L'Hopital's rule. All right, so L'Hopital's rule. So I'm going to abbreviate LH L'Hopital's rule here. So now I need to find the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. So here I need to make sure that I use the product rule. So remember to use the product rule here. So that means that the u is x and the v is e to the 3x. So u prime is 1 and v prime is 3e to the x. So what do I have here? Well, I have, all right, in the numerator, e to the 3x, then plus 3x e to the x, and then that will be minus the derivative of x, so don't forget about that, that's 1, and then all over the derivative of 1 is 0, and then the derivative of cosine of 2x will be minus sine, well 2 sine of 2x. So if you want to write the 2 out in front, you can, but I forgot to do that. So Now, this simplifies to limit as x approaches 0 of just e to 3x plus 3x e to the x all over 2 sine of 2x. And now you need to check for 0 over 0 again. So check for 0 over 0 again. So this will be for 0 over 0. So e to 3 times 0 plus 3 times 0, e to the 0, all over 2 times sine of 2 times 0. So that will be, well, what is that going to be? That will be, oh, I didn't write the minus 1. Whoops, minus 1. that, that should, that would have really did me in, right? So that will be 1 minus 1 over 2 times 0, so that's still 0 over 0. So that means I need to use L'Hopital's rule a second time here. So let's use L'Hopital's rule a second time. So I have limit as x approaches 0. And then for this part right here, I am going to need the product rule again. All right, so try to just make sure that you remember to use the product rule again here. So the u is 3x, the v is e to the x, and then the u prime is 3 and v prime is e to the oh, I for some reason I think that I forgot to write the 3 in the exponent, but yeah, there we go. I forgot to write the 3 in the exponent. So this should be 3e to the 3x. I have no idea why I forgot to write the 3, but that really did not change this. It's still 3 times 0 over there. But anyway, there we go. I don't know why one of them had a 3 in the exponent and the other one didn't, but there we go. So we have the derivative of e to the 3x, so that's 3e to the 3x, and then the product rule for 3xe to the 3x, so that 3e to the 3x, so that will be 3e to the 3x, and then plus 3x times 3e to the 3x, so that's 9xe to the 3x, so 9xe to the 3x, and then minus the derivative of 1, which is 0, and then all over 2 times the derivative of sine of 2x, so that will be 2 times cosine of 2x. And now I just check to see if I can go ahead and substitute anything here. So let's just simplify this here first. So limit as x approaches 0 of 3e to the 3x plus 3e to the 3x, so that's 6e to 3x plus 9xe to 3x all over 4 cosine of 2x. And then we see if we can substitute 0 this time without getting 0 over 0. And actually we can, because we have 6e to the 3 times 0 plus 9 times 0 e to 3 times 0 all over 4 cosine of 2 times 0. And then this ends up being, well, this will be 6 times 1 plus 0. So 6 times 1 over 4 times 1, so that's 6 over 4, which is 3 over 2. All right, so that is the end of that's the end of this example, and actually that's the end of this section, because I am not going to talk about the other part here, and I'm for certain that if I actually checked on the homework earlier this morning, and I will show you that the hardest one that I definitely found in the homework was actually one where it was actually, let me see. Yeah, there weren't any inverse sine or tangent on there. The hardest one were sines and natural logs. So I actually looked at the homework this morning and realized that I'm going to skip that one because the homework isn't going to get up to that level of difficulty. So unfortunately then that is it for this section here. So let me go ahead and stop that.